One last comment about opens and series circuits before we check out shorts. Consider two open switches in this same series circuit. Where does the voltage drop occur? If you said anything other than across the open, you're wrong. Given a 72 volt rise, all voltage will be dropped across the open. More appropriately, which open? The answer is across the large open from node B to node C single prime. Again, if you want to think of it this way, anything touching the positive terminal of the source would be charged up to 72 volts, where anything touching the grounded negative terminal of the source would be at 0 volts. A 72 volt differential will be observed across the larger open. You note elements floating in the chasm between the two opens, i.e. nodes B single prime, R2, and node C, are effectively isolated from the circuit and have absolutely nothing to do with it, and could not be used to measure any differential in the system because they're not part of the system. All voltage is dropped across the open, being the large gap between the two open switches, nodes B and C single prime, with some actual connection to the source. Moving on, let's now examine shorts inside series circuits. A short is a low or 0 ohm resistance path in parallel or around an element. Consider our original series circuit, only this time we include an ideal 0 ohm switch in parallel with R1. With the switch open, no current can pass through the switch and all current will be restricted to the original series circuit. All our previous observations will remain true. If, however, we close the switch, a 0 ohm path is placed in parallel with R1. Think about it. When presented with an 800 ohm path or a 0 ohm path, through which would a majority of electrons travel? Undoubtedly, the 0 ohm short presents a far easier means of travel from end to end. All current will be routed around the shorted 800 ohm resistor. The resistor shorted by the closed switch effectively presents a 0 ohm resistance path, and it can be removed from consideration. With no current traveling through resistor 1, there will be no voltage drop across it. Ordinarily, the source sees a total resistance of 1.8 kiloohms. If, however, current is routed around the shorted 800 ohm resistor, the total resistance seen by the source is the series combination of the remaining elements. 400 plus 600 equals 1 kiloohm. Total resistance seen by the source is decreased. Given the same supply voltage and reduced total resistance, we should expect current to increase. If current increases, we should expect voltage dropped across the remaining elements to increase. Let's see if this is the case. Source current is supply voltage over total resistance. Substituting in our given values yields 72 milliamperes of current. Source current did indeed go up. Current through elements in series is the same. I source equals I2, which equals I3, and they all equal 72 milliamperes. You'll note no current travels through R1, but rather 72 milliamperes of current is routed around it via the closed switch. Given no current through R1, R1 will experience no voltage drop. The voltage drop across R2 will be equal to the current through it times its resistance. V2 equals I2 times R2. Substituting in our given values demonstrates V2 to be roughly 28.8 volts. Given increased current, the voltage drop across R2 understandably increased. Similarly, the voltage drop across R3 will be equal to the current through it times its resistance. V3 equals I3 times R3. Substituting in our given values demonstrates V3 to be the remaining 43.2 volts. Again, given current increase, the voltage drop across R3 understandably increased. In summary, shorted elements in series circuits effectively remove the shorted element from consideration. Given a reduced total resistance, source current will understandably increase. Given increased source current, the voltage drop across the remaining elements will also understandably increase. Think about the implications of both increased current and increased voltage for the remaining elements. The remaining elements must undoubtedly experience more power. Power is voltage times current. Substituting our given values for R2 demonstrates it dissipates an increased amount of 2.1 watts of power. Similarly, R3 dissipates an increased amount of 3.1 watts of power. R1, the shorted element, experiencing no voltage nor current, dissipates no power, effectively kicking back and letting these two suckers carry the increased load. It is for this reason shorts are sometimes dangerous in series circuits because the shorting of a critical current controlling element causes the current through all remaining elements to substantially increase and thus experience more voltage and dissipate more power. In our original circuit, all elements dissipated less than 1.5 watts each. However, in the circuit including the shorted R1, the remaining elements dissipate substantially more power and run the risk of damage if lower power components are specified. Alright, I'm hoping this discussion of opens and shorts in series circuits was pretty easy given your previous understanding of series circuit analysis. As such, let's bring this lecture to a close with one more illustrated example problem. Consider the series circuit consisting of a 16-volt source, R1 having a value of 180 ohms, R2 having a value of 360 ohms, R3 having a value of 270 ohms, and two switches, switch 1 and switch 2. As an exercise to the viewer, I invite you to solve for the voltage drop across, the current through, and the power dissipated by each individual element in the system for 3 different scenarios. Scenario 1, both switches are open. Scenario 2, switch 1 is closed, switch 2 is open. In scenario 3, both switches are closed. By all means, pause the lecture and try this on your own. If you're looking for a hint, here it is. If switch 1 is closed and switch 2 is open, this would create a series combination of all 3 elements. However, if both switches are closed, this would create a series combination of only R1 and R3. R2 would be bypassed by the switch and effectively removed from consideration. If you're tracking, you should have obtained the following results. Scenario 1 should be easy enough. With both switches open, there is no path for current. No element experiences a voltage drop, nor does any element dissipate any power. The closure of switch places R1, R2, and R3 in series with one another for a total resistance of 810 ohms. As a result, the 16-volt source pushes 19.8 milliamperes of current through this system and supplies 316 milliwatts of power. Current through elements in series is the same. I1, I2, and I3 all equal 19.8 milliamperes. As a result, R1 experiences a 3.6 volt drop, R2 experiences a 7.1 volt drop, and V3 experiences the remaining 5.3 volt drop. R1 dissipates 70.2 milliwatts of power, R2 dissipates 140.5 milliwatts of power, and R3 dissipates the remaining 105.3 milliwatts of power. For scenario 3, the closure of switch 2 has shorted out resistor 2, and all current will be routed around it. The source sees the reduced total resistance of the remaining elements R1 and R3 for a total resistance of 450 ohms. As a result, source current increases to 35.6 milliamperes, and the source supplies an increased amount of 568.9 milliwatts of power. Given increased current through R1, it experiences an increased voltage drop of 6.4 volts and dissipates an increased amount of 227.6 milliwatts of power. No current travels through R2, and as a result, it experiences no voltage drop, nor does it dissipate any power. Similar to R1, the remaining element R3 experiences increased current, and as a result, an increased voltage drop of 9.6 volts and dissipates an increased 341.3 milliwatts of power. Alright, that's about it for today. Hopefully you survived that last example problem. In conclusion, this lecture took a look at opens and shorts in series DC circuits. We learned an open anywhere in a series circuit halts all current flow, and given no current flow, no voltage will be dropped across any element. Any voltage rise will be dropped across the open. Shorts in series circuits, in contrast, remove the shorted element from consideration. Given a reduced total resistance, current through, voltage across, and power dissipated by the remaining elements increase, sometimes to dangerous levels. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.